Hi, I'm Ben-Yaakov. This presentation is entitled Getting the Input Capacitance and Input Charge of MOSFET Gate. There is a relevant video to this presentation for definition of electrical capacitance. Here is the link, and I'm going to print the link at the description section of the video that you are now watching. Now, in this presentation, I'm discussing the issue of input capacitance and charge of the MOSFET at the gate. We find quite a bit of information related to these subjects. For example, here is a table. This is for this particular transistor of ST transistor. And we see here that there is an information about the input capacitance. This is CISS, meaning that at the input, while the drain and source are shorted, the output capacitance and the reverse capacitance that is between the gate and the drain. And here are the value in picofarad. And then we have some information about the charge, like the total gate charge. And then we have the gate to source. So here we have this information here in the table. And then we have these type of plots. This is the charge to the gate, and this is the voltage. So this will be the so-called Miller plateau. And then we have also information about how the drain voltage is dropping. We see that during the plateau we have the transition of the drain voltage. Now here it's only for one voltage, and here we have it for different voltages. This is another transistor, another vendor. And there is another set of information of these plots, and this again CISS, but now it's a curve, a function of the drain to source voltage. This is logarithmic, showing here the expanded scale, you might say, the drop at the low voltage. So we have these three capacitances. So there is quite a bit of information in the datasheet about capacitances and charges. But let's consider a practical case in which I'm going to choose a gate driver, okay? So here's a table from datasheet of a gate driver. This is the onsemi gate driver, just an example. And we see that they give here the rise time and fall time, very important. But it is related to a load of 1 nanofarad, 1000 picofarad, okay? That is the test circuit looks like that. Now the question is, if I have a specific MOSFET, how would I know what is its capacitance? Nowhere here you have any information of this capacitance. Not only that, all the information is given for specific points. And what happens if my operating point is not exactly 480 volts? Maybe it's something else. Now, as it turns out, the fundamental parameters are these plots. But these are small signal capacitances, okay? They are not total capacitances, not large signal capacitances, or total, that is all the charge over the voltage, but it is a local capacitance for any given drain to source voltage, okay? This by itself is not very useful. You have to do something with it to get useful information. Now, the way it is tested, these plots are actually tested and measured. And this is done by, you might say, an LCR meter. And this is an example of how this CISS is obtained. So what we have here, the transistor is subjected to a given drain to source voltage. There is a capacitor which is shorting the source to drain per the definition of CISS. And then this voltage will be changing, so we get different points. And then we have here the gate voltage with some small signal excitation, and the current is measured here. So we get the voltage, we get the current, so we can calculate what is the local small signal or differential capacitance. So in this table, for example, we have these capacitances, we have these values, but this is for a very specific point. So here it is. This is for this same MOSFET, and the numbers for the table are 50 volts. Now, what are we going to do with it? Nothing, because this is not useful. I mean, there's nothing you can do with this information. Numbers that, well, they are in the table, but I don't see any way you can use it. And now, if I go to the charge, again, I have information about a certain point in the table, 480 volt, 16 amp, 44 nanocoulomb, say, for the total gate charge. What it is this point here on this curve, okay? Well, this is sort of an average maybe, just a typical value, but what happens if the voltage is different, and what is if the current is different in my application? Now, not only that, this is not the information I need to compare a given gate driver, because the gate driver is talking about capacitance, and this is now charge. So in the following, I'm going to discuss the question how to get the equivalent input capacitance and input charge for any given operating point. So this is information that you need in order to compare it to the data given by gate driver manufacturer. Now there are two ways to do it. One is by simulation, which I highly recommend, and then by an analytical calculation based on the datasheet, and this will be based on the plots of the small signal capacitor. Now, if you have a good model, this model is as good, and in fact much better, than the analytical calculations that you can do, because the simulation model is based on the measurement, while the plots are also based on the measurement, the plots in the datasheet, which you are going to use. So you are in fact competing with the algorithm of the simulator to solve equations. In fact, these are nonlinear equations because all the capacitances are nonlinear. So in any way you look at it, simulation is a better way to go. Of course, if the model is very bad, very approximate, then it's useless. But today, most of the models are pretty good that you can rely on them, and therefore I'm highly recommending to use simulation. Nonetheless, I'm going to hint how would you go about doing an analytical calculation. So what has to be done is really to take the model, the actual transistor you're going to use, and subject it to some signal and do some measurement and get the information that you need. For example, you can get this plot here, the gate charge and the voltage of the gate, or by dividing the charge to the voltage, you can get actually the input capacitance for any given VGS and also for any given operating point, okay, not just one particular point. So here is an example of an LT SPICE schematics to do these measurements. This is just an example. There are many ways you can do it. Here is the transistor I'm going to test. This is an Infineon 100 volt 4.5 milliohm RDS-on. I have here an input signal at 10 ohm. It is recommended that you use a resistor which is close to what you're going to use in your circuit. And then I'm sort of mimicking a half bridge. This would be like the internal diode of the upper transistor. And I'm using here a Schottky diode because I don't want to deal with high peaks of reverse current and it will mess up the waveform. So I've just put here a Schottky diode. And here is the current, which is mimicking the inductor current, the current source. And this is the voltage of the bus, which I'm going to sweep if necessary to get various values here for different operating points. And of course, I can also step the current to get any given operating current. And then I've added some online calculation. And this one is actually calculating the charge going into the gate. And this is done by using the LT SPICE operator for an integral. So I'm sort of integrating the current going into the gate. And then by dividing this charge by the voltage at any given point, I mean the gate voltage, I can get the equivalent input capacitance. This is now large signal. These are not the small signal capacitances that I've just shown in the plots, but this is the large signal, like the total charge over the voltage, and this will be the value that you'll compare to the value given by the vendor of the gate driver. They're giving again a capacitance. This is the capacitance which is relevant for this comparison. So here is a typical example of such a run. We see the input to the gate. This is the excitation. There is some rise time of 10 nanoseconds. We see the gate current, and then we see here the gate voltage. This is the so-called Miller plateau. I'm going to discuss it later on. So this is the duration during this plateau that the voltage of the drain is dropping down. So this will be like the full time. And then I'm showing also the drain current. The drain current starts when we hit the threshold. And then here we have the diode current. So what is really happening? Once we hit the threshold, the current of the transistor starts to rise. And at the same time, of course, the diode current is dropping. And by the time the drain current reaches the inductor current, which is emulated by the current source, then of course the voltage is already down and there's no diode current. This is the reverse current of the diode, and this will be primarily due to the capacitance of the diode because this is a Schottky. So theoretically, you're not going to have a reverse current, but still you have a capacitor, which when flipping the voltage, you get a reverse current through the capacitor. Using this information and changing the axis here to be the charge, and this is now the voltage of the gate, I can get this curve, of course, and this is for any particular operating point that I wish. Now, what I see here is, first of all, the capacitance at the input before the plateau, and this will be the gate to source plus the gate to drain capacitance. These are non-linear capacitance, but you see that it's approximately linear curve. And then we have the middle plateau. This is during the transition. And then we have again these two capacitances, which we are charging by the excitation through the resistor. Now, very easily, we can sweep the bus voltage and see what is the effect of the bus voltage, of the drain voltage on this curve. And what we see is that when the bus voltage is small, here it is 5 volt, then for, say, 12 volt, we have this charge, while if it is 90 volt, then for the same 12 volt, so it'll be a much larger charge. I'm going to discuss this later on in more detail. Likewise, we can also see what is the effect of the inductor. Likewise, we can also see what is the effect of the drain current. And what we see here, that the drain current is causing this curve, this plateau, to go up as the current is becoming larger. And the reason is that in order to get to the point that the drain voltage will start dropping, you have to get to the current, in our case, the current of the current source. Now, the higher the current, the higher the voltage you need at the input, because of course the gate voltage is affecting the current through the transconductance. So the higher the current, the higher the voltage momentarily you need at this point in order to reach the current of, in our case, the current source, and in reality, the inductor current. So we can get this information very nicely. So now let's see what is the reason for this plateau and what is called Miller effect, but I'm going to explain it without actually resorting to the idea of the Miller effect. Now, the Miller effect talks about a impedance that is between input and output. And there is an amplifier, there is a gain, and then you see this impedance to be larger. I'm going to discuss it in a more intuitive way. So we see that this curve of the charge and the input voltage is affected by the drain voltage. That is the swing between the transistor being off until it is going into the full conduction. I'm going to explain it in a way which does not entail the Miller effect. Now, Miller effect talks about an impedance between input and output of an inverting amplifier and how this impedance is seen when looking from the input, which is a similar situation, only we are talking here about a nonlinear effect, so it's a little bit different. So let's see how we can explain what is really happening here while we are changing the input voltage. So now we feed in a signal. There is a current through the resistor, and this voltage at the gate is starting to rise until it reaches the threshold of the transistor. And then transistor starts to conduct. Nothing really happens until the current gets to the current of this source, and then the current of the diode drops to zero, and the voltage starts to go down. Okay? Now, what about the amount of charges that we need from zero until the transistor is completely conducting with RDS on? Okay? Now, for this capacitance, we are just charging it from 0 to whatever, say 15 volts. Okay, so the total charge for this capacitor will be between 0 and 15 volts. So it's 15 times this capacitance. This is the charge that we need for this capacitor. Now, what about this one? This is more tricky because, first of all, we are charging it a little bit, and then this voltage at the drain starts to drop. To sustain this drop, we need current to pass through the capacitor. This current is coming from the input. So let's not worry about what's happening in between. Let's see at the beginning and at the end. At the beginning, this capacitor is charged. Here is VB, and here is 0. Okay? Once this process is finished and the voltage of the drain is now actually 0, this capacitor is charged to 15 volt. This is plus here to here. So the total delta V of this capacitor is this 15 plus the voltage here times the capacitance. This is the charge that you have to feed to this capacitor CGD for the full process. The higher the bus voltage, the more charge you need. So that is exactly what we see here. For a low voltage, you need little charge. For a high voltage, you need much more charge. Now, using this information, we can plot the input capacitance. Again, this is the large signal capacitance, the charge over the voltage. At the beginning, until the threshold, we see these two capacitance by their value. And then comes the so-called Miller effect, in which we have to add charge, which looks as if the capacitance is large, because we have to add a lot of charge to this capacitor until the process ends, and then we are beyond the threshold. And since the capacitance is going down, as we have seen in the small signal capacitances, then the effective total capacitor is also going down a bit. Okay, so this will be the actual input capacitance to the gate throughout the process, in this case, turn on. Now, of course, we can sweep the bus voltage and see how this capacitance is changing, and I'm not going to repeat this here. So, if I'm interested in what is really happening until the transistor starts to conduct, this will be the equivalent capacitance. This is the charge over the voltage. If I'm interested in up to this point, then it'll be this charge over this voltage. And then if I'm interested in the full process until I get, say, in this case, to 10 volts, for example, then this will be the capacitance. This will be the discharge, a little bit less than 100 nanocoulomb. This is coulomb. It's a question of units here, so let's not worry about it. And 10. So divided by 10, so it's like 10 nanofarad. So this actually clears the issue how we go about to get this capacitance that we need for comparison to a gate driver and the load which is given as a linear capacitor. Let me now just explain very briefly how we'll go about doing it in an analytical way rather than by simulation. Okay? Now, the problem that we have is that the fundamental information we have is the small signal. Okay? It's a small signal capacitance. Now, we need large signal. So, for example, If we want a total capacitance between gate and drain, which is like the total charge over the total voltage at any given point, then we can start by looking at the actual definition of the derivative or local capacitance, which is the derivative of Q with respect to the voltage. This is the definition of the small signal capacitance. And now we can take the integral to get the charge. Once we get the charge, we can divide it by the voltage to get the capacitance. This will be the total capacitance. So then you have to do it, of course, for the other capacitance. So as I have said, I highly recommend to do all this by simulation, which is by no way inferior. In fact, I think it is superior to the analytical calculation in this case. So this brings me to the end of this presentation. I thank you very much for your attention. I hope you found it of interest, and perhaps it will be useful to you in the future. Thank you very much.